Okay? Now, if you have, here's the comparable thing with logarithms. It's a little bit weird, but if you have log base 2, I'm going to say 10, plus log base 2 of 5. Up here we started with multiplication and we added the exponents. Remember, the logarithm is an exponent. Okay? You actually multiply what you're taking the logarithm of. Yep, so this is log base 2 of 50. Here, you're multiplying things with exponents in them, so you add the exponents. All right, here, the logarithms themselves are the exponents. So if you're adding them, it refers to multiplication of what you're finding the exponent of. It's that's one property of logarithms. Here's a similar property. If I have 5 to the 12th power over 5 to the 5th power, what's that equal?
5 to the 7th.
5 to the 7th. If I have log base 2 of 10 divided by log base 2, hang on, I'm writing this incorrectly. I don't want to confuse you. I mean to say, if I have log base 2 of 10 minus log base 2 of 5, what do you think I can do in that case?
Take out the log 2.
Not take out the log 2. It's not thinking. I still keep the log 2, and
2.
I divide the 10 by 5, which gives me log base 2 of 2. Incidentally, what is log base 2 of 2?
1.
1. 2 to the first power is 1. Cody just raised a good point. We're into logarithms now. Logarithms are not, I keep saying that the logarithm expression itself is an exponent. These are exponents backwards, and it's the inverse of exponents. That's all true. But there's a reason why logarithms don't get a place in PEMDAS. Parentheses, exponents, multiplication, division, addition, subtraction. They don't behave normally in terms of the order of operations. They don't get to follow the distributive property. Which means, Cody, you actually can't take out the log base 2. You cannot distribute or undistribute logarithms. Okay? That's important. Please don't start doing that. Otherwise, that will be bad.
You're blowing our minds.
All right. Here's the most important one. And here's something that sped up calculations immensely. Okay. We're going to take another look at this property. And I'm going to say I have log base, log base 10, I'll leave it like that, of 8 cubed. Okay, log base 10, thank you, Emma.
You have an exponent on an exponent?
Well, this is actually log base 10 of 8 cubed like that, so I'm not really raising the logarithm to a power. I'm raising 8 to a power and then finding the logarithm of that. All right, if I do that, this is the same thing as log base 8 times 8 times 8, right?
Is 8 like an exponent, or do people just write it a little higher?
I'm not sure what you're asking. I'm not meaning to have 8 be an exponent anyway in this case. So if it looks like I'm writing it higher or something, please tell me.
So it's log 8 to the 3rd.
Well, yeah, it's log 8 times 8 to the 3rd. But this rule says that addition becomes multiplication. Well, this rule works forward and backwards. So if I have log 8 times 8 times 8, no, I can't add them like that. I can split it like this. Log 8 plus log 8 plus log 8. Now, I just said that you can't do anything fancy with the distributive property here. So it's not like I can factor out the log 8 and then get log... No, I can't do that. To do that, I'd have to be able to like take the log out of each one and then add the 8s. It's 3 log 8. All I can say is I have 3 log 8s now. I can't say that that's... and that won't be the same thing as log 24. Now, I started with log 8 cubed. I wound up with 3 log 8. That pattern will actually always hold. Logarithms let you take something in an exponent spot and bring it down as a coefficient. Logarithms change multiplication into addition, they change division into subtraction, and they change exponents into logarithms. If you don't have a calculator and you're working with lots of huge numbers, cube roots, decimals, all that sort of stuff.
Then you're screwed.
Well, yeah, unless you were good with logarithms. Because then instead of figuring out something to the 10th power, you just had to multiply its logarithm times 10. Instead of cubing 8, which wouldn't be that hard, you just had to find the, pardon? 512, yeah. But if you were unable to do that, if we were dealing with bigger numbers, you would have a table that would have the log of 8, and you just had to multiply that number times 3. With 8, that's probably a waste of time, right? Because you know 8 cubed is 512. If you're dealing with larger numbers, like astronomical distances, if you're trying to figure out, it's 1650, and you're trying to figure out if the Earth goes around the sun or vice versa, this was real handy. I'm going to write these 3 rules generally, and then we'll do a couple of problems with them. The 3 rules in the most general form are, if you have log of any base, so I'll use n for that, of a number, plus log of any base, as long as it's the same base, that part's important, as long as it's the same base, just like when you're multiplying x with numbers with exponents, they have to be the same base to do anything, you will get the log of the same base of those 2 numbers multiplied. And this works forward and backwards. This is known as condensing the logarithm. If you start here and turn it into addition, it's known as expanding the logarithm. If you have log of the same base a minus log of the same base b, you can condense this subtraction into a division problem. Or if you start with division inside the logarithm, you can expand it to 2 logarithms being subtracted. Okay? Now, last one is if you have log base a, log base n, I want to be consistent, of a, and that's raised to an exponent that I'll call b. You can bring the b down in front, and it goes from being a coefficient, it goes from being an exponent to being a coefficient. You can do that forward or backwards. All right. I'll tell you what you'll have to do with this, and maybe a little bit on why you have to care. I'll start with this one, because it's my favorite.
Yeah, what do we have to care?
Short answer, Algebra 2 is a high school graduation requirement almost everywhere. That's the short answer.
That's helpful.
Yeah. Longer answer is my usual one. It depends on what you're going into for a living. Okay. Use this example a lot. 5 to the x equals 125. What is that? 3. How'd you know that?
5 to the third equals.
Because you know what 5 cubed is, exactly. You don't have a process to solve that. Okay? If you think about it, you've never learned a process to solve that. Actually, like if I tell you x plus 5 equals 10, what's x? 5, because all of you know that 5 plus 5 is 10, right? Mm-hmm. But if you didn't know that, what would you do?
Subtract 5 from both sides.
Right, subtract 5 from both sides and you get x equals 5. Let's go back to this example again. Well, that's a tricky one. If you didn't know that 5 cubed was 125, what process would you follow to get x by itself?
Start multiplying 5 by 5.
Well, that's a trial and error process. That's actually won't get x by itself still.
Cube root
That's
both
not an
sides.
algorithm. Cube root both sides?
Well,
Why would you pick cube root? Because you know 5 cubed is 125.
because I know 125 has a
Could you
square
X root?
so the next step would be cube root.
And you keep trying and trying?
I have an idea.
What?
We use a logarithm.
We use a logarithm. Cody and Layla just gave very smart ideas on how to guess the answer, but they were still guesswork. They weren't a process to get x by itself like you know how to do for this.
So we were just trying to prove you wrong.
Thank you. I appreciate that. Now, here's what I'm going to do, okay? If I don't have a calculator, there's 2 ways to do this. If I don't have a calculator, I'm going to take the log base 5 of both sides. If I don't have a calculator, we used to have, when I learned this in high school, there weren't calculators, when I was a child,